Well, thank you everyone for coming, and thanks to the organizers for letting me talk about one of my projects today, which is on Minkowski functionals. Minkowski functionals as a tool to study non-Gaussianity in cosmological fields, and in particular, how we extend the formalism to CMB polarization. My name is Duque. I'm a postdoc in INFN in Torber Data, and this is some work that I've been doing in collaboration with the people in the cosmology group there. In particular, it's not there it is. In particular, Alessandro, who is also in the conference, in case you see him. So this is the outline for my talk today. I will start with an introduction on Minkowski functionals. Then I will talk about how we apply them to polarization, CMB polarization. I will mention other applications of Minkowski functionals. Then I will briefly describe the software we have developed and published to do this. And I will summarize my conclusions at the end. So let's start very simple with Gaussian fields. We know that Gaussian fields are easy to describe if our physical process is given us a Gaussian field like the CMB, which is at least very nearly Gaussian. Anomalies messed up, but it's very nearly Gaussian. Then we can essentially obtain all the information we can just from the 2-point correlation function, the typical power spectra, or in the CMB, the angular power spectra. Now, what happens if we take this tool, which is a very powerful tool, and we apply it to a field that is not Gaussian? Nothing, because the power spectrum is blind to non-Gaussianity. So it will give us information, but not all the information. And furthermore, it's not telling us that there is more to learn. Because of this, the cosmological community has adopted and even developed new statistical tools in order to extract this extra information. These tools include, of course, the 3-arc 4-point correlation function, bispectra, trispectra, but also things like extrema statistics, distribution of maxima, distribution of minima, distribution of clusters, distribution of voids, these kind of things. Statistics like Betty number, persistent homology, things like inference directly from the field level inference, some approaches for machine learning, and in particular, Minkowski functionals, which describe the geometry and topology of the field. Each of these can be the topic of an entire workshop, so I will only talk a little bit about Minkowski functionals. And just a word of FNL. So non-Gaussianity is usually studied through FNL, and this parameter is, of course, very important because it will give us a lot of information, but it's not the only way to study non-Gaussianity. And non-Gaussianity is an infinite dimensional space, so we need a lot of tools to study different kinds of non-Gaussianity. So in particular, Minkowski functionals are high-order statistics. This means that the information in the Minkowski functionals is not contained in the 2, 3, 4 endpoint correlation function. There is something else in the Minkowski functionals. Okay, so what are they? Let me define them. Take your favorite field. CMB temperature, density of galaxies, an image of your favorite galaxy, whatever it is. And let's say that this top field is your favorite field. Okay, we define a threshold, we call it U, for example, 2 sigma, and we take the regions from the field that are above this threshold, above 2 sigma, and those are the white blobs that you can see there. This is called the excursion set at 2 sigma. Now we can describe this excursion set with 3 quantities: the total area, the length of the boundary of these blobs, and the number of regions minus the number of holes. This is a topological quantity called the Euler-Poincare characteristic. It's not very. The thing is that we have 3 independent quantities that can describe this. And this, of course, is a function of the threshold. You can do it at every threshold, and you will obtain a curve telling you the Minkowski functional of your field. Okay, so you may say, yeah, I can compute this on my field, but what is this telling me about Gaussianity? The thing is that Minkowski functionals are very accurately predicted for isotropic Gaussian fields. This means that the expectation value is known, and the variance It's also known, and it's very small. I'm not going to enter on why this is the case. We can discuss later if you're interested. But the thing is that there are 3 factors that influence this theoretical prediction. The first one is the threshold. Of course, the value is different at 2 sigma, 0, whatever. But these are very well-known functions. The second one is the manifold, the space where we are studying this field. For example, if you're studying your field on the sphere, like the CMB, this is just the area of the sphere, 4 pi. If you're studying this on a 3-dimensional box, the volume of your box. If you're studying this on a sky, but with a mask, like we have to always do, this is just the volume, the area in this case, of your observation. So this is 4 pi times your sky fraction. There is no mixing, no leaking, no coupling of any kind. This is completely independent for all the thresholds and all your fields. This just depends on your total footprint. And the last quantity is just a number that you can think about it as like the correlation length of your field. This you compute it once on your field, and all your Minkowski functionals depend just on this one. Just to show that I'm not lying, and these are actually easy formulas, this is the case for isotropic Gaussian field on the sky, and they look like those plots, right? So these are small functions, easy to check. So Minkowski functionals have plenty of applications because since we know what should be the value in the case of Gaussianity, we can test for deviations from these predictions. This was done already in the Planck papers, in the isotropy and statistics from the last release, where they test in a blind way where there is some deviation. Of course, they don't find any blind deviation because the CMB is very nearly Gaussian, but these tools can also be obtained, can also be applied to fields that we know are not Gaussian in order to extract that information. Because that information we cannot extract with the power spectrum, we have to use other tools. And this was done, well, it's a very active field of literature, but this was done, for example, by Euclid, where they analyzed the convergence map of a galaxy in a forecast. And the convergence map, of course, is not a Gaussian field. It traces the distribution of matter. And this distribution of matter is giving us a lot of information. In this plot that is a little bit opaque by the something, they produce a forecast of different cosmological parameters of what will be your uncertainties just with the power spectrum in blue or just with Minkowski functional in yellowish. So these provide orthogonal information, which of course you can then combine. Minkowski functionals have also been applied to foregrounds because they are very non-Gaussian, very anisotropic. And they can also be applied to the large scale structure. For example, galaxy distributions. And again, this recent paper by Duque forecast the power, the Fisher matrices, for only the power spectra in blue or only Minkowski functionals in yellow. And then, of course, you can combine them. So I hope I convinced you that these tools are useful for cosmology. And now I will describe how we are applying them to CMB polarization. CMB polarization has the characteristic that it's a complex field on the sky. So what I was describing before of the excursion sets is not really defined. What does it mean that 1 plus I is larger than 2 sigma? That's not really defined. So we have to find a way to define these excursion sets. The first one is just analyzing the modulus of the polarization. So this is P squared, this is perfectly well defined, it's a scalar field on the sphere. And since it's a real scalar map, we can do Minkowski functionals as I have described. The only difference here is that P squared is not a Gaussian map, it's more like the sum of 2 Gaussian maps. So it's like a chi-square map with some spin effects. So taking this into account, we managed to produce the theoretical predictions, which look, again, very easy. We have verified with simulations that both the theoretical predictions and our software seem to be correct. And we were in fact amazed by how close they are. In the top plots, you can see the three Minkowski functionals. In the top plot, you can see the value. And then in the second row, you can see the residuals. And, well, maybe with this projector it's not visible, but the order of magnitude is like 10 to the 4 times smaller. So, indeed, this prediction seems to be working very well. Our code seems to be producing the correct results. So we apply this formalism to Planck. Planck polarization data, unfortunately, is not isotropic because of the noise. The observational strategy means that the noise is anisotropic. So we cannot compare it with the isotropic predictions. If we do, it's like 50 sigma difference. It's really anisotropic. But we can compare it with realistic simulations that include this observational strategy. If we do, we observe, of course, no significant deviation from the Gaussian hypothesis because, well, again, this is mostly noise, and noise should be Gaussian. But we are looking forward to apply this kind of formalism to future missions like LightBear, so kind of things, and see what happens there. Okay, but I just told you that the polarization field is complex, and we want to extract all the information we can from this field. If we analyze any scalar projection, we are losing information. This happens if you analyze P, if you analyze E, B, Q, U. If you analyze even E and B independently, it's still not enough with higher order statistics. It's enough with the power spectrum, but not with higher order statistics. So the way we do this is by adopting this formalism, this function that has been recently proposed in the mathematical literature and well studied there. So in this case, we see polarization not as a complex field on the sphere, but as a real field on a higher dimensional space, three-dimensional space. So this is just a function that depends on three variables that are essentially the point in the sky and the direction. And it just tells you the polarization in that point and that direction. So this function is real. It has a very particular and well-defined structure. So the Minkowski functionals were difficult to find here, but we were able to do it, and they look like this. This is a three-dimensional space, so there is another Minkowski functionals. There is always dimensions plus one. So we have four Minkowski functionals, and again, they look, simulations and theories, they look essentially the same. They are very accurate. Okay, so let me talk about a couple of applications. The first one is that we want to apply this to galactic dust. And there has been already a couple of talks talking about foregrounds in polarization. They are very difficult to simulate because the non-Gaussianity is definitely not trivial. Non-Gaussian is anisotropic, and it's not clear how you should create realization of this kind of box. And of course, I have no idea either. So I just Giuseppe. And what we are doing here is to analyze different models that have been already proposed in the literature and assessing how not Gaussian they are. Which one is the most non-Gaussian, which one is closer to data, and what kind of non-Gaussianities they present. And in fact, we observe that it's different. I'm not telling you what models they are, because this is still preliminary, but stay tuned in the next couple of months. And yeah, as I say, this is with Giuseppe. So a small parenthesis is that on my other project, I work on the cosmic web. We have developed a catalog of cosmic filaments. So if you're interested in this, feel free to have a look. I think it's producing good results. It has like high redshift, machine learning, all of these buzzwords. So feel free to have a look. And I mentioned this because I am interested in large scale structure as well. So of course, I'm interested in applying Minkowski functionals to the large scale structure. Now, the elephant in the room is the large scale structure is not Gaussian. But there is a lot of information in the non-Gaussianity. They could be primordial, if we're lucky, consequence of inflation. But of course, most of them will be late universe non-Gaussianities produced by nonlinear gravity, baryonic effects, neutrino physics. And of course, this will be dominant. So there are a lot of questions to be answered here. For example, can Minkowski functionals help distinguishing both? Can we include the effect of gravity, of nonlinear gravity, in the theoretical predictions, like it can be done in the power spectrum? Can we use Minkowski functionals to constrain cosmological parameters? With simulations, we can. Can we do something more effective, more efficient? And of course, how do they compare to other statistics? Are they better for certain theoretical models? Do they present different degeneracies? Are they more robust to these different systematics? These things have already been started to be studied in the literature on Minkowski functionals. And there are some promising results, but there are still a lot of questions to be answered here. So it's a very, very nice field if you're interested. And not only for Minkowski functionals, in general, for all higher order statistics, these questions, they're still working on this. And of course, they can have many other applications. We're working on some. If you have any idea, I would love to hear about them. Let me just, in this last section, talk about the Python package we have produced. It's called Minkowski. And it is fully documented and modular. We have a module for the theory, where you can produce the theoretical predictions for different kind of fields, like Gaussian, squares. We have a module for data, where you can use it to obtain the Minkowski functionals of specific maps, specific fields that you have. For now, we have implemented Kilpix maps fully, and we already have a working version for NP arrays in both 2 dimensions and 3 dimensions, which should be ready soon. And we also have a statistics module, which of course we're focusing on Minkowski functionals, but we have also implemented things like maximum distribution, minimum distribution. If you have anything in mind, please contact us, and it will be nice to include more. All the modules are easy to use, easy to expand, hopefully. Feel free to check it out in the GitHub. And just very quickly, to show that I'm not lying to you, the thing is that if you load your map, and you load your map until here, you can obtain your Minkowski functionals, both the data and the theory, with essentially 4 lines. And I think it's very intuitive to use. Okay, so my takeaway points. First one is that Minkowski functionals are useful tools to study non-Gaussianity, and they can be applied in the early and in the late universe. We have expanded this formalism to CMB polarization, which we hope to be useful with future data. And we do that in 2 different ways, with p-squared, but also with the full information spin map. And we have created this Minkowski package that I hope is useful to you, and is the application of Minkowski functionals to the cosmological community. So that is all. Thank you very much.